Today, examples. You have gotten all the theory from the classical bone graft, so now it's just a matter of training for you guys. So I'll go through some examples here today. Start very simple, mechanical problem. So we have given a velocity source acting on a spring, hitting a mass, M. The mass is on a table, and here we have some friction, resistance, inertance, and a spring. So that's our system. Draw the bone graft, find the equations, program it, simulate it. Okay, this one should be now rather straightforward for you guys, shouldn't it? No colors. Okay, we can deal without it. Start by identifying points which has its own unique velocity. So here we have three separate ones. We have a point here. He is attacked by a flow source. Then I have a 1 here with mass attached to it. And finally, I have a floor where x dot equal to be 0 to be thorough. Then we can use take the ground with us as well. Here, a spring I insert with a 0 junction like this. And the resistance here also with a 0 and R. So there you have the raw total bone graft for this problem. And now simplify. We remove the ground, it doesn't move. 0 power on this bond here. Then this 0 also can be removed. It has just 2 bonds, they doesn't do anything. So the resistance can be hooked on directly to the 1 junction. And this point here, the location of this point, can be skipped. Just remove the 1 junction. We don't need it. If you want to know the position of that point, okay, then you should leave the 1 junction as it is. It's nothing wrong with it, but to find the state equation, you don't need it. So I simplify the following way. Source hitting directly the 0 junction where we have a spring, continuing to a 1 junction where I have a mass and I have a resistance. So that will be the simplified bone graft for this case. Everybody with me so far? That's good. Now start with the causal strokes. As always, you start with the sources. Here I have a flow source. He gives the velocity. So the stroke has to be here. If you mix this, then everything falls to pieces. So this one has to be correct. Just remember, it's always the effort that goes towards the stroke. So here for a flow source, then I need the flow to go this way into the system. Hence the stroke has to be to the left. Okay, this stroke doesn't dictate anything further in my bone graft, so now I have to choose. Take one of the C or the I element and choose the integral causal form. So I choose that one for the C element. Now this 0 will dictate. It has to be, the last stroke has to be away from him. He needs only 1 stroke towards him. Now this 1 junction over here, well, I still have a choice. He's not dictating anything, but I choose, of course, the integral form on the inertance. Then the 1 junction here has gotten the 1 and only stroke away from him, and the last one is then given. So it's a causal system, second order. Now we start to annotate. I know the flow from the source. That's given as a well-known function. And the effort there, I don't care about. Cross it out. Next, I have two energy storage elements on the integral form. So here, Q dot circle, and on the other side, Q over C. For the inertance, I have a P dot on the effort side, and on the flow side, P divided by I. And now for the rest, we have to sort of look at the junctions, who dictates what. For the one junction here, okay, that's where you're missing a stroke that dictates the common flow, P over I. Aha. Then I have P over I for all bonds connecting this one junction. And for the resistance then, if you know the flow, then you find the force R multiplied with P over I. And then finally, for the zero junction, common effort, who dictates the effort? That's where you have the stroke. Okay, that's this Q over C. Has to go here as well. So there, the Bone Graft is completely annotated. So where is my equations? I should have one equation involving Q dot and another one involving P dot. That's what I have because they have circles around them. They should be possible to find somewhere. So let's now try the summation rules. Around zero junction, the sum of the flows has to become zero. Now Q dot, that's the flow out, has to equals flow in. And X dot S positive, while the flow P over I, he goes out, minus. Now on the other side, the sum of the efforts around the one junction has to be zero. Hence P dot that goes out equals the efforts that comes in, Q over C, and then minus the resistance force R P over I. So there you have your two equations, and they should now be easily programmed and plotted. Any questions so far? That's okay. Good. So let us make a little script. Let's see, clear all, close all, CLC. Can you read this in the back? It's a little small maybe, but hopefully it's okay. Good. How do we solve this one? Well, I have some constants here that I have to choose. Let's say now we have the mass, for instance, I. He can be 1. I have a spring. He can be 1. Resistance. He can be 1. Any other parameters that we need? No, I don't think so. So then it should be possible here now to write brutally t comma y equals ODE 45. So here I jump directly to an ODE solver for this one. That might be a bad idea. So when you're struggling with a problem, maybe it's not the smartest choice to jump directly into ODE 45, because if something fishy is going on, something strange is happening, he explodes, he gives you nothing back. You get a whole bunch of red text from MATLAB saying the weirdest things that nobody can understand. So you really get nothing. So maybe you should program this one with your own first order Euler scheme. That might be much wiser. here I don't care about that. I didn't jump directly to the OD45. I have to have a function. I have to have some time span. Well, we can always write a Tmax up here, just for cosmetic reasons, like that. And then I need initial values. I have two equations. Q, that's my first, P is my second. So initially I can say both of them are 0. Then we plot the solution. Hopefully we'll get one. And I put on a grid on the display. So that should be my main program. We can save this one as untitled. That is a good name. Now I need this function. But inside the function, then I'm going to need the same parameters that I've written here. So, of course, it's a question: do you want to write your constants in the main program or in a function? I would recommend writing them in the main program, first entry in the main program, and then you transfer them to your function using a global sentence. I will recommend that one. If you have these constant statements in your function, then he has to execute them every time you access this function. Okay, this function, he returns the derivatives, the left-hand side of your equation system, equals func, and then t comma y. And then we insert the global sentence like that. Next, you should tell him what to return. In other words, the number of equations that you have. So here, 2 equations. Next, the vector y, that is all your unknowns at a certain time. So you should rewrite it using q and p. Now my first equation, that's equation with q, hence q will be given as y number 1. And p must then be y number 2. So it's quite essential here to keep track of the sequence of your equation. This is my first one, this is the second one. Hence, in the y vector, the first value should be a q, second should be a p. Same goes with the call from the main program. First initial value is my q, second initial value is my p. So don't mix it up. Okay, then we return the first derivative. Q dot equals x s. I don't have xs, so we have to create that one. Minus p divided by I. And the other one, it should be q divided by c minus r multiplied with p divided by I. Something like that. And then we have to create the velocity source. Now let's make it simple. xs. Well, let's make it very simple first. 0. I don't have any source. Then what will happen? This point doesn't move, and I start everything is 0. So this one now will just be a control of the dummy solution. Everything equal to 0. So let's try this one. And I just get a straight line, 0. That makes sense. Okay, let's try with a different source. Give him a constant velocity. What will happen then? Constant velocity, pushing this to the right, but then the spring might start some oscillating things here. Let's see what happens. Save this one and run. Yeah, something like that. So everything levels off around the value of 1. So here, as I said before, when you really don't know the values for these parameters entering your problem, set everything to 1. Then you know you have a time scale where most of it will happen in a time scale of 1. So choosing here a maximum time of 10, you cover most of the physics directly. So that's always smart. So what's happening here as a steady state solution, if we continue a little bit, T max to be, say, 30. Okay, it really levels off to 1. That's another check then you can do. What's the steady state? Steady state meaning nothing should move. Then this P here has to be constant. We have a balance here. Okay, then P divided by I. What's that in mechanics? P, that's the momentum. That's mass times velocity. Divided by mass, okay, then we are back with the velocity. Hence, the velocity has to be constant, equal to this spring force, which then, of course, is 1. Here, this one should be 0. Okay, then you have a balance here. Then the velocity equals the source velocity, as you can see. So a steady state control, always smart. Any questions to this one? Okay. Now look at the problem. Here I have modeled the resistance as a linear damper. So that means I have used a force proportional to the velocity. But what if I remove the oil film or whatever it is, and now look at Coulomb friction? Can I manage this one? Coulomb friction, what's that? Coulomb friction, you will have something standing on the table, and then you push him, try to push him. And you will then have, if he moves, you will have a resistance force here, and F resistance equal, it will be a material parameter depending on the surfaces here. If it's rubber or ice, then he can be big or small, multiplied with the weight of this mass times gravity. And of course, this force, he will act in the opposite direction of the motion. But what if he is not moving? I mean, you have an object standing on the table, and then you push him. But you don't push him so hard. Just push him a little bit. He doesn't move. Okay, what's the resistance force? Of course, the resistance force will adjust himself so that the sum of the forces equals 0. This value is only valid when he is in motion. When he is not moving, the force will actually adjust himself to balance out, so you have no motion at all. Program that one. Okay. Then what do we do? So now I have a resistance that is definitely not linear anymore. I have the flow sort of into this R, but this is not correct anymore. So how should we write this one? Well, actually, I have to write it as a function. Fr, he will be a function of what? Well, it's a question of the motion, actually. of the velocity. And here I then have to remove the linear force that I had from the old resistance, and now insert an FR as a function of P. So this will now be my program. Everybody agrees on that? Okay. So let's try to change this program. I remove the resistance. I don't need that one anymore, but I need a mu mg, of course. And then resistance we don't need, mu mg instead. So what now in my function? Mu mg. And down here I remove the force that I had and insert now FR. So I have to find this resistance force depending on the velocity. So here I have to do something, and this is actually rather criminal. It's not allowed, but sometimes we do it anyway. I use an if sentence inside a function to be used by ODE solvers. Very bad idea. But let's do it anyway. If the velocity equals to 0, then what? FR equal to, and then I had to write something tricky. Let's see, it's the smallest one of the absolute value of Q divided by C, the spring force, or this mu mg force, like that, multiplied with the sign of the variable Q. This force should always act towards the motion. Then if this spring sort of is squeezed in together, it will be negative. Then he will act as a positive source. So now with the minus here, that should now be correct. Sine, that's a function in MATLAB. He will return +1 if it's positive, -1 if it's negative, 0 if it's 0. So sine, let's just give you the direction. If that's not the case, that means he's actually moving. Okay, then I have the force given as a sliding resistance force, just a constant force. So FR then should be something like mu mg multiplied with the sign of the velocity. End. There we have it. And again, I just have a constant velocity, and then let's see if we can capture this motion. So I save this one. And we try to run it, say for 20 seconds. Something is wrong here. Undefined function sine? Doesn't he have sine? Ah, it's a Q. Thank you. Sine. Let's see if that helps. There we go. So what kind of motion is this? Looks a little strange, doesn't it? Let's zoom in a little bit. We can have a Tmax of 10. We can change this value a little bit to 2, just to see what happens. Yeah, a little bit more dramatic. So now let's see if we can interpret what's going on here. The first line, that's the blue one, that should now be solution to my first equation. So that's the displacement over the spring. So he's getting bigger and bigger, the displacement, meaning bigger and bigger force. But you have to have a certain force before he starts to move. So now 2 and 2. Then finally he starts to move, and then he moves quite fast. Then, of course, the spring will now be released since he's in motion. It's dynamic, so he's sort of catching up with the spring. And then he will slow down and all the way down to 0 again. So now it's a question down here. Has he stopped? Will I have a period here, some seconds, milliseconds, where he's not moving or not? And to see that, we can zoom in. Nah, not much. Actually not. So here is now a question. Should I believe this solution? Well, I have used an TEP4240, so it should be a fourth order accurate. But it's this if sentence. He really doesn't like it. I can show you if we plot here and using pluses instead. And you can see how he works. So when things are moving nice and slowly, and he doesn't need many points, but look at here. In this case where I have this if sentence, you sort of change the rule of the game in the middle of the simulation. So if you zoom in here, you can see how he has to work to resolve this one. He needs a whole bunch of data points to get it correct. So the system here is actually quite stiff. So let's try with some of the other solvers then. 23S, it's also for stiff solvers. You see, he's much faster. He doesn't need that many points, and he finds sort of the same solution much faster. Now you can try with 15S, that's another stiff solver. And if I recall correctly, we had some trouble with this one. He doesn't really get it. He gets it in the end, but he had to use a tremendous amount of function calls to find what was happening here. So in the initial state, that's not a problem, it's just 1 point. But here he uses a lot of effort to find the solution. So, and also here, if you play with different numbers, changing this this coefficient mu to something else, you risk not getting a solution at all. So it's a very bad idea, this if sentence, changing the equations in the middle of the stream. Very bad idea. So what should you do? Well, you could use your own first order Euler scheme. That might actually be much better for this case. Then it's not a problem using an if sentence. But you have something else, another option you should be aware of with MATLAB. Something called an event. It's possible then to call an ODE solver and tell him, solve this problem, the function, from time equals 0 to sometime into the future. But if something happens, something that you define, then stop. As an example, you write bold ODE in the command window. Yeah, you get a warning here from 15S, so it doesn't really get the solution correctly. So try write bal ODE. Ball ODE. So that's a simulation of a bouncing ball. You just drop him and then he bounces from the floor, and they remove some of the energy every time he bounces up from the floor. So you see he gets lower and lower the amplitude. So it's just a bouncing ball. And here they solve this problem with ODE 45. But you have to use an ODE then into the future, and you don't know. When you start here, you don't know how long time it will take before he hits the ground again. That's uncertain. So you just instruct the ODE solver, simulate until y gets, the height gets 0 again, and then stop. And then you have the time and everything at this point. Then you just switch the velocity to be positive, remove some % of it, and then you do another simulation. So you could do the same here using this event handling. You simulate until something happens. Then you change your function, and then you can simulate further until something else happens. And if you want to look at the source code, how this is done, you can write in the command window, you write edit space bal ODE. Then you have the source code for this function, how it is done. So it's a lot of cosmetics here in the beginning. So just to make the graphs, they actually use here ODE 23, not 45, but that's okay. All the way down here you find two functions. First, the simple function that we always use in an ODE solver, f as a function of time and y. So he returns two derivatives, gravity of course involved, and the other one, that's just the velocity equals x derivative. Then you have another function based on events. And here you actually specify the event that's going to take place when the simulation should return. So that is really something quite strong actually when you have the problem like we have here. Instead of using an if sentence, then we should use the event. So we should start here with this problem. If I start with 0 velocity for him, okay, then I should simulate until what happens? Until the force gets balanced. The spring force will be now bigger than this, this possible friction force, and then he will start to move. Then I should stop the simulation, because now I have sort of changed the equations. And then simulate further until he stops again. That would be much, much better using event handling. So have a look at this ODE, bal ODE example, how this is done. That's really something worthwhile. So if sentences in the function for ODE solvers, bad idea. Becomes very, very stiff. Of course it does. If you think about it, you change the rules in the middle of the simulation. ODE hates that. Really has to try to resolve what's happening when you switch, sort of, you change the equations. He doesn't like it. Okay, any questions to this example? I can put out the source code here so you can play around with it yourself. That's okay? Okay, let's try some other examples then. Let's take an electric example. So here I have a source, an effort source, E0. Here I have a resistance, and then I have a branch, I have another resistance, capacitor, then we go back here, and here in parallel I have a third resistance. So here we have R1, R2, R3, and a C. Find the state equation. Okay. So how do we do that? Well, elements in electric circuits are inserted with a one junction because the flow goes straight through these elements. So for the source, effort source, we will have a one junction. Going up, finding resistance number 1, so one junction, R1, continuing, and then I have a logical branch. Here we use a zero junction in all these crosses because the voltage, the effort will be the same regardless which way you are looking. So real branches are done with zeros. Going down here and one junction, R2, continuing down another one junction and the capacitor, further down and finding another 0, and then go back to the 1, and finally here I have a one junction, R3, and hooking up with the 0 junction. So there you have the raw bone graft. Now for electrical circuits, we choose anywhere we like. You choose ground level somewhere. Doesn't have to be at the bottom, but we choose it somewhere. And we say the voltage at ground level is 0. So everything that's directly connected to ground can be removed. You have 0 power in those bonds. So this bond is removed, this one is removed. Then this 0, he doesn't do anything. This one also 0. And then this one junction, he has only 2 bonds, can be removed. This one junction also can be removed. This one junction, now only 2 bonds, can be removed. Now what are we left with? Better be careful here. Let's rewrite it. Effort source hitting now a one junction with R1, continuing with a 0. From this 0 I have 1 hitting R3 directly, then continuing to a one junction where I have an R2 and a C. R2 and the C element. So that should be my simplified bone graft. Everybody with me on that one? Nope, no protesting. So then it must be correct. That's good. Now start with the annotation here. Causal strokes. I have an effort source. So yes, we start here. The effort hitting into the system, stroke towards the system. Then that doesn't dictate anything. Okay, I have a C element over here, so of course I choose then the integral causality for him. And that doesn't dictate anything either. And then you see the problem. I can't go any further. Nothing is dictated here, nothing is given. You are not allowed to choose for the resistances, so you're stuck. This is then what we call an under-causal system. And for under-causal systems, what was the solution? Well, you add a virtual element, a virtual C or a virtual I. And where should you add it? Well, a virtual I element, he will have the causal stroke away from the junction. So if you add a virtual I element, I virtual, the stroke is here. If you add a virtual C element, the stroke will be here. So it's up to you what you need here. And here, well, we have 3 different junctions. You can actually choose any one of these 3. So say we choose the first one, the one junction here. For this one junction sort of to be fulfilled with the one stroke away from him, I need a virtual I element. So if we do this, virtual I element here, then the stroke should be here. Then he is fulfilled. He is happy. He has found the one and only away from him. Then the rest has to go like this. And now for the 0 junction, he has gotten 1 away from him. Well, actually, that really doesn't help, does it? So here I'm going to need another one, don't I? I mean, I have 1 stroke here, but this stroke, it doesn't dictate anything for this 0 junction. So it really didn't help. That was too bad. Okay, let's try something else then. I try an I element here. Virtual IV, stroke here. Okay, then this one junction has found the one and only away from him. Has to be like this. And again, this doesn't dictate anything for this 0. Again, no, it really doesn't work all the way. So I try the last one as well. Let's see, like that. So on this 0 junction, I add a virtual C element like this. Then my 0 junction has gotten the 1 stroke he needs towards him. The rest has to be away, 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 and away. And then you see everything is nested out quite nicely. So then for this one junction has to be away, for this one junction has to be away. So for this problem, a virtual C element did the trick. Then you need only 1. If you had chosen a virtual I element, then actually you needed 2 of them. So that would also work actually, but of course much simpler with just 1. Any questions to that one? That's okay. Then we continue with that one after the break.